To what extent do considerations of the functioning of the brain impact in relationship to criminality? The defence of being mentally unstable in most of the courts of the English-speaking world are referred to as the Mcnaughton Rules. Mcnaughton tried to kill Sir Robert Peel in 1843. He missed him and instead shot dead Peel's personal private secretary. It was regarded as automatic by Queen Victoria, and the rest probably of the United Kingdom, that he would be hung within the fortnight. That did not happen. The reason it did not happen was the greatest defence counsel in the United Kingdom, at that time, Alexander Cockburn, had just read a book by the most distinguished psychiatrist in the United States, Isaac Ray. And Isaac Ray came up with the extraordinary idea that a person might be able to distinguish between right and wrong, but still commit a criminal act because of a lack of self-control or because of impulsivity. And eventually they were incorporated into the so-called Mcnaughton Rules for this kind of defence. Now, what does brain science tell us now in the context of self-control and in the context of impulsivity? Well, for example, I'll show you here a case of what we call utilitarian behaviour, where someone sitting across the desk being interviewed in relationship to some difficulty picks up the pair of glasses you put on the desk and tries to put them over their own existing set of glasses. And as they do that, they say, "Look, Max, Bennett, I'm having trouble here. I know what I'm about to do is stupid, but I can't help myself." This is an act of utilitarian behaviour. Another act of this kind, called anarchic limb, is when the patient suddenly lunges out and tries to grab you. And as the hand is midway, they say, "This is absurd, this is very aggressive, but I can't stop myself." If you do magnetic resonance imaging of the brain of some of these patients, what you can see is that there's considerable bits here, what are referred to as the supplementary motor cortex, and surrounding areas missing or invaded by a lesion of some kind. So there is an inductive correlation between something as overt and large as that and this incapacity of self-control. But it can get much more subtle, as shown here. In this case here, there is a very small lesion indicated by that circle here in much the same area of the brain, the supplementary motor cortex. And this patient, in this particular example, when asked to move their eyes from left to right, and then just before they start to move them, told to stop, couldn't stop. The eyes would continue to move, and then eventually they caught up with the command. Whereas a normal person, when told to move their eyes from left to right, will start to move them from left to right, and you can leave the command for a long while, tell them to stop, and they'll stop straight away. So this is a subtle example of a lack of self-control. The lesion is there, it's correlated with this subtle level of lack of self-control. But impulsivity is a much more aggressive act, and people suffering in psychiatric tests from impulsivity are suffering from something which can lead, in many cases, to something quite dreadful in the criminal repertoire, such as murder. Those that have been on amphetamine or on excessive amounts of cocaine generally strip out part of the grey matter in part of the brain here called the orbital frontal cortex, just under there, shown here. And this is the part of the brain up here in the orbit of someone who had impulsivity and who had stripped out parts of the grey matter here in the frontal lobe, orbital frontal cortex. That could be correlated with their impulsivity. Now, Mcnaughton undoubtedly suffered from schizophrenia. That, though, wasn't defined until 60 years after Mcnaughton died. In the case of Mcnaughton, it's on the file, it's easy to read. He not only had hallucinations, but he had the delusion that the Prime Minister of England was trying to kill him. And even though he knew it was wrong to go and try and kill the Prime Minister of England, that was the only mode of his defence. It fell into the Mcnaughton Rules exactly. Now we know that if we do scans on the brains of someone who's developing schizophrenia, again, we can detect loss of grey matter all over the cortex, as shown here. This is magnetic resonance imaging type scanning. This is a development of a child which already had unusually schizophrenia at about the age of 12, and the red regions here indicate that between that age and around about 20, when the schizophrenia became totally florid, large amounts of grey matter were missing, as indicated in the red regions there, as compared with a normal child developing in that age group. So again, we get an inductive correlation between these changes in grey matter in the brain and this condition of schizophrenia. But the point I want to make is that in all these cases, and all the thousands of cases that come into the Brain and Mind Research Institute in Sydney, they are all overtly of some kind of behavioural defect of one kind or another. You can pick it up almost immediately they walk in the room, so sometimes it'll be more subtle, come out under a Hamilton depression test involving questionnaires and things like that, but it is overt in their behaviour that something's gone awry. Then you go in and do magnetic resonance imaging or non-invasive imaging, and maybe you'll find some of these lesions. But the bottom line in courts of law and in the entire treatment panoply of what we do in the Institute, you are dealing with human beings in the behavioural repertoire of the normal life of each one of us, and in the case of them, something has gone awry, and that is explicit. And neuroscience has nothing to say about what has actually produced this behaviour other than showing that grey matter has occurred. But you don't first go to magnetic resonance imaging and then say this person has got impulsivity, because losses of grey matter in different parts of the brain are correlated with a whole different range of different kinds of behaviour. It is the behaviour of the human being in the richness of the society in which they're embedded that is the criteria of what has gone awry in their condition. The second case I want to talk about, and the third case, involved levels of criminality that could arise as a consequence of you having the responsibility to remove the support system of someone either in what we refer to as locked-in syndrome or in what is referred to as the vegetative state. Perhaps the most famous example of locked-in syndrome is that of Bowlby, who's is shown here. Bowlby was the patient that was responsible, in a sense, indirectly for that famous film of Schnabel's called The Diving Bell and the Butterfly, which happens to be the name of the book which Bowlby wrote by doing the only thing someone with locked-in syndrome can do, and that is either move an eye or blink. Everything else, all muscular, all volitional effort is gone with the exception of that condition. And what Bowlby did, as many of you will know, is that with his assistant here, he would blink when the French alphabet was read out to him at a time when he wanted her to record the word in the alphabet at the moment he blinked. And she would write that word down. And as a consequence of altogether of 285,000 blinks, he produced his book, The Diving Bird and the Butterfly. Now, what that book shows is this, that even though Bowlby, all he could do was blink, he had a richness in his psychological repertoire. He could think, he could remember, he had affectations, he could perceive. He did this whole range of things which we normally refer to as the mind. Mind your step, look where you're going. Keep that in mind, remember that. Be mindful, think about the whole thing. This word mind is a synonym for these ranges of psychological capacities, and there's no doubt that Bowlby had a mind which was functioning at a pretty good level indeed. You do not then have to go and do brain imaging on Bowlby to find this rich repertoire of humanity that resided there still in the corporeal body, which had decayed a great deal as a consequence of the stroke he'd received here in the bulbar region of the brain. But if you do brain imaging, then you can see in a normal person, for example, very high levels of metabolic activity. Here we see the oxygen levels. Same thing happens with glucose levels, energy levels here. These levels here are about when you're doing nothing, like many of you are now because you're bored with what I'm saying, you're half asleep, and so you're doing virtually nothing. You're not thinking about what I'm saying, you're not looking about what I'm saying, you're thinking of lunchtime only a little bit. That's the resting brain. This is a resting brain, and the levels of activity there, as indicated by metabolism, are about 90% of maximum. Now, a gentleman over there just scratched his nose like that. A volitional act, which involves activity probably in the motor cortex, in which case you'll maybe get a couple of % more of activity in the 90% you can see here as a consequence of the motor act. However, if that gentleman now gets appendicitis and has to go to hospital and undertake an anaesthetic, what happens is this. Here we have the brain, as I showed it to you previously, very high level of metabolism. He's sitting there quietly doing nothing. But under the general anaesthetic, in this case chlorelase, when this energy level drops as the anaesthetic takes over to about 40% of the level found here in the normal resting brain, then you become unconscious. Unconscious, what do you mean by unconscious? Mysterious word, unconscious. What Peter Hacker and I defined as two kinds of consciousness. Here, in transitive consciousness, the person didn't wake up during the operation. When his gut was open to get the appendix out, he didn't suddenly sit up. Before that incision was made, he was pinched, he was talked to, he was tapped on the head. There was no reaction at all involving an intentional act. Nothing at all. So the general anaesthetist has said, he's down to 40% level, let's go for it, and he went the incision. However, if you put him under deep chlorelase, you can knock that down from this level here to about 5%. Way, way down. And you can bring him back up again. If you're a good anaesthetist, you can bring him back up again after the operation. So what was the case with Bowlby? Well, in locked-in syndrome, what you see is this. Over here, we have what I indicated to you in my first imaging thing. That is a normal person, very high levels of energy activity indicated there. In locked-in syndrome, as indicated here, what you've got is something which is quite similar to that. If you look at the minimal conscious state, that is, as the anaesthetic has dropped you down from these high energy levels to about 40% of the levels, well, then you can see, obviously, you've come down. Now, you're going to hear a lot, you've already heard a bit, you're going to hear a lot about these things, these energy levels and these different kinds of non-invasive imaging techniques. Well, the greatest worker, I think, critical work in this field, Logothetis, said in the famous scientific journal Nature just a few months ago that there are now about 25,000 papers published using this. And both he and I think that nearly all of them are nonsense. First of all, there is a grave level of dishonesty that goes on in the neuroscientific community. It's not overt. It's not like that gentleman in the House of Congress is here 24 hours ago saying you lie. It's not quite as bad as that, but it's getting in that direction. And why is it? It's because what's being measured nearly all the time in these imaging, in what was called the BOLD effect, the blood oxygen levels, which I think the last speaker used a BOLD effect slides, what you're measuring is activity, not at all. You're measuring blood flow. This concept of using blood flow to measure, to indicate something in the brain was discovered by Sherrington 105 years ago, and I don't think the field has progressed enormously since then. Because what is now happening is people are not talking in any papers in the journals about increases in blood flow. They're talking about neuronal activity and increases in neurons and this sort of stuff. Now, there's a tremendous number of difficulties in this field. To couple blood flow to what neurons are doing is enormously difficult to know what's going on. And we don't, to be honest, know what's going on. Furthermore, the neuronal activity in some particular part of the brain is only a smidgen of the activity that's going on in a part of the brain. For example, most of the brain doesn't consist of neurons at all. It consists of glial cells, and they are very active cells in terms of oxygen consumption and other matters. And I can go on and on and on about the difficulties of this. But let's pretend it's all kosher for a little while. Okay, so what we've got here is we've got the locked-in syndrome. We've got Bowlby here. Now, doing a scan like that on Bowlby and believing that it's all fair dinkum and kosher is not proving that Bowlby is human, that is, has a corporeal body and has a mind, that is, a range of these psychological capacities of thinking, remembering and feeling and perceiving. Bowlby showed that in the best conceivable way because his book includes how sensual he found the nurse that walked in and helped him, how he loved seeing his kids, how he very much liked being pushed out on the bed onto the balcony and received the early morning sun. He did the sort of things that you and I do as human beings, and that showed unequivocally that he was almost fully human. except for the volitional difficulties of having everything locked down because of his bulbar stroke. So we don't need to do this at all. And in fact, we don't know what this represents. We don't know what all this energy that's going on in a normal resting state is about. We certainly know it's about something to do with blood vessels, but that's about it. Let me take on, though, a much more difficult situation. Let's look not at this thing called locked-in syndrome, but the vegetative state, of which perhaps the most famous is Karen Quinlan, shown here, who at the age of 21 went to a party, got stuck into the drugs and the alcohol at the same time, collapsed, respiration collapsed for a short time, taken to hospital, was declared to be in the vegetative state. Then the hospital wanted to turn off the support system. Certain people protested about that. The hospital wasn't going to enter into criminal exercises, did not turn off the support system until the courts decided 20 years later that they could. They then turned off the support system and she survived for another 15 years through her own respiratory brainstem activity, which is not unusual as residual activity in someone in the so-called vegetative state. The Royal College of Physicians defines the vegetative state, amongst other things, as one in which the patient does not respond to audition, to visual clues, to sensory, somatosensory as we call it, clues, to rubbings and bangings in an intentional way at all. And that was the case with her. Okay, so if we do brain imaging on her, what do we see? Well, people who have the vegetative state look like this. They don't look like normal. They don't look like locked-in syndrome. They don't look like minimally conscious going out in the general setting. They look like that there. So what we've now got there is a situation where we've got a very minimal, I think, level entirely of it. But that's not the basis for saying that Quinlan was in the vegetative state. The fact is that she did not show any intentional activity at all in relationship to behaviour as we would if we were partly asleep and partly not asleep and someone was scratching us on the head and bumping us and talking to us and matters of that kind. However, recently, Owen has carried out a series of experiments on people in the vegetative state, which bring up a whole new range of interesting questions. And in order to try and be honest, I'll present them to you. And that is, what he did was, he took both patients in the vegetative state, as well as controls here, and he said something about tennis to them. Now, here is a normal person, just sitting there. He says tennis, and then the imaging in this, what is called functional magnetic resonance imaging, which is this blood level business, which I have great suspicions about, up came this area called the supplementary motor area, which is not surprising. If you say tennis, or if you say axe, or if you say leave the room, or if you say anything to do with action words, you carry out actions, there's a plethora of things you can do, up will come the supplementary motor area. If you went to this patient that was in the vegetative state and said, let's go and play tennis, up came a bit of supplementary motor area. Now, this was a vegetative state. However, the first thing I want to mention to you is that, as often happens in these imaging experiments, which is never commented on in the last several years, except by one of the founding fathers of magnetic resonance imaging, Bob Schulman, who makes a lot of it, and quite correctly so, you have subtracted out here 90% of the activity that I showed you in my first slide about the imaging of the brain. That is, you've thrown out 90% of what's going on, whatever that might be. And you've just taken this little 3 or 4% extra bit. All right, we'll put that aside. But it really comes up as important here because in the case of this patient, you had nothing to throw away because there was nothing there at the 90% level in the first place. And yet the claim is there's a little bit of lighting up there. Now, of the 24,000 or 5,000 papers in imagery, there is an enormous amount of confusion and contradiction, although amongst the cognoscenti, they believe there's enough agreement in certain areas to hold on to. All right, let's go along with that. What's all this about then, that this patient that is in the vegetative state, as I've defined, but when you say tennis or something like that, up comes an area similar to that in a normal person. Now, I'm going out on the wire here, since I've been somewhat aggressive in relationship to imaging, I'm going out on the wire and I'm going to say this. If you take a normal person and you present them with a word on the screen, the word here might be note here, and then a few milliseconds before that, you present them with a scrambled set of material like that on the screen, and then a few milliseconds after that, a scrambled set of material on the screen like that, then what happens is, when you ask them what the word was, they don't know what you're talking about. They don't know that there was a word presented, nor do they name, of course, being able to name the word at all. If, however, you don't do that, but you take the particular word and instead of on either side putting screens which are full of scrambled material, you put screens which are just dead blanks, and you ask them what word they saw, they'll say, yes, I saw this word, and they'll name the word. The scrambling on either side within milliseconds of being presented with the data is such that they can't grasp that a word has been shown. So what does imaging show if we do this experiment? What imaging shows, if you can trust it, and since I'm caught in a bit of a contradiction here, I'm talking as if I do trust it, what imaging shows is indicated here. When you use the non-masked words without the scrambling before and after the word I showed you, certain areas light up as indicated here in the green, here, here and here. If under conditions where the scrambling wasn't used before and after, but a blank screen was used, and as a consequence of blank screen you were able to see the word, you said you saw the word, then here an area lights up, that is, there's an increase in blood flow, and over here there's an increase in blood flow. And this is similar to certain areas which come up here for the normal person, that is not the normal person, I should say the person who sees the words. In other words, when you are not aware of things, then things are going on in your brain. And in fact, for those of you who are not conscious of what I'm saying now, who have lost all attention to what I'm saying, are no longer aware of what I'm saying, things are still going on in your brain which are related to what I'm saying, except that those things in your brain have not reached levels of awareness where your attention has been grasped. Now, I think that's possibly what's going on in the locked-in syndrome. You're bringing in certain of these almost reflexive components which are unrelated to awareness or attention at all. And I comment on that in the following context. My hobby at night, in order to get to sleep at midnight, is to write books in philosophy and history. And one interesting set of articles which I thought I wrote concerned what was referred to as the spinal soul. This dominated neuroscience as it then was in the 18th and 19th century. And please don't look too carefully at this rather nasty image, because it is of a beheaded frog. This is a very old image. It's of a beheaded frog here. And this frog has had its spinal cord touched a bit with a pin, and it goes through this reflex action. But not only that, we've known since the time of Aristotle that if the head's removed of the frog and we brush that side of the limb, if this limb here is not tied up, the limb will come across and scratch the other side. It'll do that. Now, that gave rise to the concept that there must be a spinal soul. That is, there seemed to be an intentional reaction to the sensory stimulus, which was touching the bone. Now, all that disappeared, not necessarily on logical grounds, in 1900, when Charles Sherrington, one of the two geniuses of neuroscience of the 20th century, showed that there were networks here in the spinal cord which would fire off in such a pattern that when you stroked that side of the limb there, you would get the wiping reflex coming over like that. And after that, everyone relaxed. And I kind of think, putting my head on the block here, that if there's anything going on with this imaging, then really what we're looking at in this case of locked-in syndrome is that kind of thing, only it's happening in the cortical level rather than down here. The final point I want to raise in relation to criminality is this. Your High Court 3 years ago had to deliberate on the question of whether juveniles in half the states that make up your union can be sent to the electric chair for a gross criminal act. Now, the judgment which came down, I thought, was spot on. They were given a large number of submissions from the community of neuroscientists. What was pointed out to their honours was that during normal development, something which I discovered in 1972, just for your benefit, in normal development, between the ages of about 5 and 20, there are very large numbers of changes in grey matter. So that the grey matter when you're about 7 or 8 is more than it is when you're about 20 years of age. There's a gradual loss of grey matter that occurs there. And I'll come back to that in a moment. So you can hardly say that someone at the age of 14 back here and still hasn't got the mature level of grey matter is mature if you're a neuroscientist thinking in neuroscientific terms. And in fact, all of that was quantitated as shown here. I won't go through all this, of course, but the levels of grey matter loss, for example, in certain regions of the brain, up here in the frontal regions, about 20% is lost between 5 and 20. Up here in the parietal regions, about 30% of the grey matter loss in normal development. This is not a schizophrenic person. This is normal development. Now, if you carry out a range of about 8 or 10 different psychological tests during different periods of development, you can't correlate most of those with any of these changes in grey matter. Now, that doesn't mean that I don't believe, as all good neuroscientists do, because it is the fundamental principle and basis of our particular discipline, and that is that we will always find changes in the brain which are concomitants, which are inductively related to changes in our psychological capacities of thinking, remembering, feeling and perceiving. So I think as time goes on, I won't go through these histograms. These are 6 psychological tests over different age groups. There's starting off at 6, it doesn't settle down to about 15. Here's one, starts off at 8, it settles down about that age there, so that's quite a good correlation actually with the changes in grey matter. Here, the whole thing settled down, this particular test, at the age of 10. That was a very bad correlation because things don't settle down in terms of grey matter loss until you're about 20 years of age. So, what did the High Court judges come to? They came to the conclusion that nobody under the age of 18 can be sent to the electric chair in the United States of America. And in their very long deliberations, they made no reference whatsoever to neuroscience. And the reason for that was that you just look at kids aged 15 and you ask any parent, is your 15-year-old son mature? And you get very definite answers right across the community spectrum, right across all racial groups. Furthermore, if you ask groups of psychologists who do all the tests and psychiatrists do all the tests and ask them about the behaviour, they'll say the same thing. 15-year-old, not mature. 18-year-old, maybe. But 15-year-old, forget it. So the judgment was no more going to electric chair before 18 years of age because there's no question that you're not mature at that age. They did make one little addendum, though, and they said that it's kind of a pity that neuroscience, which is drawing correlations between changes in brain structure and changes in maturity, has no causal connection between the two, even when there might be correlations between changes in a particular psychological state and changes in grey matter. And that's true enough, although Dodd, who only died 18 months ago, couldn't find causal connections when he first set forth the hypothesis that lung cancer was due to smoking. Now we're just catching up with that. So the lack of any causal basis is not all that bad if you get good correlations, but the correlations themselves, I believe, are irrelevant because it's in the behaviour of the child that it's important. It is the human being acting out in society that is the basis of all these considerations. Now, I've been very hard on something that I've spent 50 years on, namely neuroscience. I've been doing experiments for that period of time, not 25, but 50 years. And I've been, if I might be a little bit of self-aggrandisement here, typical of me, I've been, 30 years ago, president of the Australian Neuroscience Society. 20 years ago, president of the International Society for Autonomic Neuroscience. 10 years ago, I gave the opening plenary lecture at the World Congress of Neuroscience. I'm not an idiot when it comes to neuroscience. So I'm not going completely off the stack when I say take a lot of what you hear about imaging with a grain of salt. But what does neuroscience tell us that is really valuable? It tells us something of immense value. And I want to leave this on a positive note, which I'm going to spend the next 50 years of my research on. Here is the brain. No sniggering, please. Here is the brain. I've talked again and again about changes in grey matter. in the brain, particularly when I was talking about the Mcnaughton Rules. What is grey matter? Well, grey matter is made up of the following cells. It's made up of the lining of the ventricles here, the epithelial line. It's made up 65% of glial cells. It's made up of endothelial cells wrapped around the blood vessels from which we get most of this imaging these days. It's made up of axons, which got the processes of oligodendrocytes, which become diseased in things like multiple sclerosis. And it also contains neurons. And of course, the 20th century, as was the 19th, was totally neurocentric. And I think that was a mistake, because I think the glial cells are coming into their own. But let me just deal with this point. The aspect of grey matter which is changing in the diseases of interest to me is the neuropath. The neuropath consists overwhelmingly of the connections between one neuron and another. This is one neuron's process. There's other processes coming through. And here one neuron sends and abuts onto another neuron. There are about 10,000 of these connections on every neuron. And these connections are called synapses, and that's been blown up here. The neuropath consists of these synapses, overwhelmingly. So, in grey matter loss, in the diseases of interest to me, in psychiatric diseases like schizophrenia and like bipolar manic depression, and like at least 5% of you suffer from, that is major clinical depression, mood disorders, that's what changes. These are diseases of the synapse, not of the neuron, which pack up in things like Parkinson's disease and dementia, although everything packs up in the way of synapses eventually. But these psychiatric diseases are diseases of the synapse. So that if, with magnetic resonance imaging or some of these non-invasive imaging techniques, we can pinpoint areas of the brain which have gone awry so that we can no longer express one of our psychological capacities, so-called mind, that is, thinking, remembering, feeling and perceiving, then we've got a handle on something we might do to put right what has gone wrong. We can develop animal models, for example, of things like clinical depression. They're not humans, they're rats, and then they might have one element, and that element might not have all that much to do with depression. But we're working them up. And so we can now do pharmaceutical interventions on them, we can do scannings on them, and we can see what we can do in relationship to putting right this loss of grey matter, which is inductively correlated to what has gone awry in human behaviour. But in the end, it isn't the neuroscience, it isn't the synapse, which is the observable that concerns us and which has gone awry. It's human beings. Thank you very much.